ready to go back in time? Okay, as Cameron nicely introduced, I will be talking about rewinding orbits of galaxies in our nearby universe. But first we're going to go back to some of the basics. So if you've heard this, we'll refresh your knowledge, and if you haven't, hopefully you'll learn something new. So we're going to start out by just looking at our place in the universe. So we're going to start in our Earth. This is a nice visual that's been put together by the American Museum of Natural History. We're zooming out. We're going very quickly. If you want the slowed down version, it's on the internet. Okay, we're going out to our solar system. We're going to the constellations. The sun's true brightness. We're going to get to some of the confirmed exoplanets. There's definitely some experts on those. Don't ask me questions about them, but definitely find them. We're going out of our Milky Way and we're stopping at the nearby galaxies. So this is my laboratory. So we're going to take a little bit of a closer look at that. But first, we're going to talk about, this moves, what is a galaxy? So for the purpose of this talk, I like the definition. A galaxy is a system of millions or billions of stars, gas, dust, and dark matter held together by gravitational attraction. So you've probably seen pictures like this if you're an astronomy fan. On the left, you're seeing many images from the Hubble Space Telescope. These are all primarily spiral galaxies. You can see there's a lot of structure in them. They're different colors. They have spiral arms. Some of them have a bar in the middle. There's a whole diversity of galaxies here. But this is a nice zoomed in version, and on the right side, I'm showing an image from the James Webb Space Telescope. This is of a galaxy cluster. And here you can now see in the scale of the universe, you see some galaxies are closer, some galaxies are further. You see more diversity in their colors, their shapes, their sizes. But ultimately, we see there is a really broad range of galaxies. And today I'll be mostly speaking about the lowest mass galaxies and essentially the faintest galaxies in the universe. So not quite this scale, but I'll get to the rate of what we're talking about. Before we get to the small galaxies, I just want to go over the anatomy of our own galaxy, the Milky Way. So in spiral galaxies like the Milky Way, on the left you're seeing an artist's illustration based on real data. And you're seeing, I've put our location of the sun, so we live in one of the spiral arms around the Milky Way. And on the right side, you can see the edge-on view of a galaxy like the Milky Way. So we have a bulge or a nucleated cluster of stars in the center. Again, there's a location of the sun. There's a disk in the center, and there's a couple of other interesting smaller stellar clusters that live around the Milky Way. That's a lot of what I'll be talking about today. But for context, because we're going to be talking about on vastly different time scales from what we're used to thinking about here on Earth, I just wanted to give you the definition of a galactic year, which is how long does it take for our sun and the solar system to do one full rotation around the center of the galaxy. And that takes about 225 million Earth years, right? So this is already big scales, but we're going to go even bigger in a second. So what I think about on a pretty regular basis are satellite galaxies, which are sort of self-explanatory based on their name. But satellite galaxies are galaxies that typically orbit a larger, more massive galaxy. So much like our moon goes around the Earth every 30 days, these satellite galaxies are orbiting around what I'll refer to as a host galaxy. So there's many of these out in the universe. We'll look at some of them in just a minute. I've purposefully drawn these orbits, or the idea of an orbit here, to show that we of course know that the moon goes around a closed orbit around the Milky Way. It does it over and over again. It goes through a very similar path every time. On the other hand, satellite galaxies, some of them don't even pass around their host galaxies in one full time in the history of the whole universe. Others do it many times. So we'll talk a little bit about the diversity of the orbits of these satellite galaxies as well. So while there's an analog here of the moon, Earth, or even the Earth-Sun system, there are some differences when we go to the galactic regime. I've also put a little bit of a time scale on the bottom. So of course we know that we're on the days time scale when we're talking about the moon orbiting around the Earth. But when we go to these galactic scales, what I think about, the units of time I think about are gigayears. So that is 1 billion years, a 1 followed by 9 zeros. Okay, so you're going to see some references to billions of years or gigayears, often abbreviated as GYR. This will also be relevant for the next talk, so you're ready for that. But this is the time scales we're talking about, and because we're talking about these very, very long time scales that are much beyond what we can fathom here on Earth, this is why we need to use lots of models and simulations, and that's really where my expertise comes in. So we'll get to that in a bit. Okay, but here is essentially my laboratory. So this is again an artist illustration based on real data, but this is what we refer to as the local group of galaxies. It's very cleverly named. So this is our nearest group of galaxies. The Milky Way, our own home galaxy, is in the bottom right. You see that spiral galaxy in the center. And in the top left, you see the Andromeda Galaxy, our nearest neighbor. If you're a Mac user, you've probably seen a galaxy wallpaper at some point in the history of Macs. That's the Andromeda Galaxy. Okay, you can see it with telescopes from the ground. If you're in a dark enough place, you might have seen it already. A thing to note about both of these galaxy systems are that they're surrounded by these small little fuzzes of light. And these are the satellite galaxies. Now, all of the known satellite galaxies are not shown here. So this is just a subset of what we know of now. Part of that is because this discovery timeline is moving at a very rapid rate. So back in the year 2000, we only knew of about a dozen satellite galaxies orbiting around our own Milky Way. Fast forward just 10 years, that number doubled to about 25 satellites have been found by the year 2010. Fast forward again to 2020, and we hit all the way up to 50 satellites. Now, the reason these numbers are climbing so quickly are for a multitude of reasons. One is that our technology is getting better. So we have better telescopes. They can get to fainter and fainter galaxies, and so we can find more of them. We're also searching new parts of the sky that haven't been searched to those faint levels before. And our algorithms for actually finding these in data is getting better as well. So there's a sort of an algorithmic technique that is also improving. So this has been a really exciting field to work in because I started my graduate career in 2014. So I remember, running to my PhD advisor's office and saying, "Did you see there were 14 new satellite galaxies posted today?" So it's been a very fun place to work in. And this number, I wrote 50 plus satellites because it's only going to keep going up. So there are upcoming observatories like the Rubin Observatory down in Chile that is going to help us find many, many more satellite galaxies around the Milky Way and other galaxies. And in general, if you're wondering whether satellite galaxies are rare or not, we think they're a pretty ubiquitous phenomenon. So we think that many Milky Way mass galaxies should have, and we have actually found these, many satellite galaxies of their own. Okay? So they're a very popular thing you'll find when you look out in the universe if you can get to the right faintness limits. Okay, let's look at a couple of pictures to give you a sense of the diversity just amongst this population. So in the middle, again, I'm showing a Milky Way-sized galaxy. On the left, there's a picture of a galaxy called the LMC, which stands for the Large Magellanic Cloud. It is the most massive satellite galaxy orbiting our own galaxy. So that's for scale. In terms of mass, the LMC is about 10% the mass of the Milky Way. Okay, then on the very right side, I'm sure some of you in the back, and maybe even some folks in the front, are probably not even convinced there's something in that image. That is one of the faintest galaxies that we currently know of, okay? So this is kind of the broad range, just in a picture of what we're finding, right? So of course there's many things in between, but hopefully the image on the right gives you a sense of why we have to have very sophisticated algorithms and extremely powerful telescopes to be able to find the stars in those galaxies and actually identify them as a galaxy of their own. Okay, so let's get to what do I do with all of this. So I said that the local group is my laboratory, and so I collaborate very closely with folks who use observatories like the Hubble Space Telescope or data from the Gaia spacecraft or the James Webb Space Telescope. Those folks go out and take measurements of how fast these galaxies are moving, at least in an instantaneous sense. So you do have to wait quite a while to actually see a galaxy move, and it's definitely not something you can see with your eyes by just going back and forth between two images. So there's also fancy techniques for actually seeing the difference across the images that we're looking at. But regardless, my collaborators measure these motions, and then I put them into an orbital model. And what that orbital model does is it models the approximate mass that's in a host galaxy, so either the Milky Way or Andromeda in this case. It models the approximate mass that's in these smaller, fainter satellite galaxies. And then we use some physics and we do some numerical integrations. This is all computer-based, to try to determine where these satellite galaxies were at past epochs in their lifetime. And so the lines I've overlaid on top of this image are actual predictions I've made. They're not always all lined up exactly with the satellites you see here, but they are correct with respect to the host galaxies they're orbiting around. What I'd like you to notice in the bottom right is that there's really not a lot of order to these orbits, right? They're not all neatly going around in circles or even ellipses. You see lots of them just look like a streak across the image. That's because those are the satellites that haven't yet completed even one full passage around the host galaxy, the Milky Way in this case. If you look very closely, you have a good view, you can probably see some near the center of the image that do look like they kind of wrap around the Milky Way a few times. I'll show some other versions of this so that you can get a better sense of that. Okay, so this is what I do. Now, why are satellite galaxies important? There are many reasons. I'm just going to give you 3 today. You can ask me about more later. But first and foremost, satellite galaxies are the building blocks of more massive galaxies. Okay, so they contribute to the growth of galaxies like the Milky Way over cosmic time. So let's look at this image on the left, which is again another nice artist illustration based on real data, where they've shown a host galaxy like the Milky Way, a nice spiral galaxy in the bottom, and you see this sort of ribbon of stars that's traversing around that host galaxy. And this is essentially a snapshot of what we can observe in reality, and what this process is showing you is a satellite galaxy being torn apart by the gravity of its host galaxy. And in the process of that happening, these stars are being ripped away from that satellite galaxy's central body. And so you're left with what we refer to as stellar streams. You'll hear more about these in the next talk. These are things that we can actually observe and have observed many of in the universe. So we can see this process of galaxies being completely disrupted in real time, just not, we can't play a movie of it unless you have a simulation. So that's one of the reasons why satellite galaxies are important, and we think galaxies like the Milky Way have merged with these kinds of satellite galaxies more than a dozen times already in its lifetime, and this will continue to happen as the universe continues to age. Again, this is something that happens, we think, around all galaxies, and so this is one of the ways in which galaxies grow, both in mass and in size, over time. Sometimes when galaxies merge together, they even completely change their shapes. So if 2 spiral galaxies merge together, they often turn into what we refer to as an elliptical galaxy, which is just a really bright spheroidal group of stars. So there's a lot of really interesting things that happen when galaxies merge together. This is one of those, at least in the regime of satellite galaxies. Okay, I'm going to show you a movie on the right side that will show you simulated data of a Milky Way-like galaxy. And what you're going to watch is the growth of a galaxy like the Milky Way. So I'm going to quickly describe what you'll see. You'll see a very bright ball of light at the center. That's going to represent our own Milky Way galaxy. And then you're going to see these blobs come in from the outskirts and start to pass around that host galaxy. And in the process of doing so, you'll start to see a more realistic representation of these stellar streams forming in time. So in the middle, you have that bright bulge that's representing our galaxy like the Milky Way, and you see these ribbons of stars. It's a satellite that just flew in, it comes back out, it loses a lot of its stars in the process, it goes out of frame for a moment, some of them come back again, and in doing so, they'll also form another, what we refer to as a wrap of a stellar stream, so another one of these sort of elliptical shapes of stars. But this is really illustrating to you over the age of the universe how this process happens over time and how often it happens for a galaxy like our Milky Way. You can also find movies like this online. You can watch them many, many times. They're real fun. And here's the credits if you want to take a look. Based out of Rutgers University. Okay, let's talk about another reason why satellite galaxies are important. Well, you've probably heard the term dark matter. So satellite galaxies, we believe, move through the dark matter halos of their host galaxies. So what does that mean? On the left, I'm showing an image where at the very center, the very small ellipse is representing the disk of a galaxy like the Milky Way. So it's just the spiral part of the disk, it's where all the stars live. What I'm showing in the outermost circle is where we think the extent of the dark matter of a galaxy like the Milky Way, how far that goes. So this is already giving you a sense of scale. So in comparison to the galaxy's disk, the extent of the dark matter halo is about a factor of 20 more than that. Okay, so we're talking about a really massive reservoir of essentially invisible matter, because we can't observe it directly, around these galaxies. And so the satellite galaxies are important here because the satellite galaxies are moving through that medium that we can't observe directly, but we can infer by gravitational attraction. So the white small circles are representing different satellite galaxies around a Milky Way-like galaxy. And as you can see, they're in that bigger white circle. And so as they're passing through, we can learn about where is the dark matter and how is it distributed around host galaxies like the Milky Way. Fun fact, we also do think that these satellites have a lot of dark matter in them as well, but I'm not going to talk more about that today. And also to give you a sense of how much of a galaxy like the Milky Way is made up of dark matter, at least when you're talking about weighing a galaxy like the Milky Way, about 85% of the mass of a Milky Way-like galaxy is in dark matter. So we can't see 85% of our galaxy. The rest of it is composed of the stars, the gas, the dust, all of the things that we can actually detect with various kinds of telescopes. You might be asking, well, how do we know that dark matter exists? Well, one line of evidence is the following. I'll just go over this one. There are many more. So one reason why we think dark matter exists is because of Vera Rubin, who I mentioned earlier, because there's the Rubin Observatory that will start taking data and help us find many more satellites around the Milky Way and other galaxies based down in Chile. Okay, what Vera Rubin did back in 1970 is she measured the speed of stars in our neighboring Andromeda galaxy. So this background image is actually real data from her paper from 1970. And what she was doing is she was looking at stars moving outwards from the center of Andromeda. So going from the brightest part to the dimmest part. And as she was doing that, she was measuring how fast they orbit around the center of the Andromeda galaxy. And what's drawn on here in the blue and yellow curves is what was observed. So there's a blue line showing you what was observed. You see that it kind of peaks where you're in the brightest parts of the galaxies and then plateaus. And then the yellow shows you what's expected by the basic laws of physics. And what you see there is a big peak in the very inner regions, but as soon as you sort of hit the edge of the galactic disk where you don't see any more stars, we expect that the speeds will go down because we don't think there's much matter out there, and so the stars are not really they're not feeling the extra influence of any additional mass. However, because of this gap, which she has observed not just around the Andromeda galaxy, but many other spiral galaxies, so she's done this experiment multiple times, she inferred that because of this gap between the observations and expectations, that there has to be some more invisible, very massive matter in the outskirts of galaxies. So this is one reason why we believe that dark matter exists, even if we don't quite understand exactly what it's made of. Okay, so going back to what I do. So now that you've got the landscape of why these satellites are exciting to study, where they are, how many of them there could be, what I'm showing in this movie on the left that's just going to bounce back and forth over the last 2 or 3 billion years. This movie is showing you the orbits of 50 of the satellite galaxies around the Milky Way. Of course, it's very simplified, so every dot represents a satellite galaxy, and the lines that they're following are their expected trajectories backwards in time. So again, we see that there's a broad diversity here. Hopefully now you can see that some of them, at least the ones closer to the center, are really wrapping around the Milky Way multiple times. Many of the ones in the outer part of the frame are sort of just coming into the vicinity of the Milky Way and not completing one full passage, at least in the time frame that I'm showing here, which is just 2 to 3 billion years. Some other things that we've learned about satellite galaxies is that unlike the planets in our solar system, they don't all orbit in one plane, right? So we think that the planets all go sort of around the sun, and they don't have a lot of inclination, right? So they're all in one sort of disk around the sun. That's not the case here, and we don't think it's the case in general around other galaxies either. And finally, maybe my favorite part about studying this is that we've recently started to realize that several of these satellite galaxies have really similar orbits. So about a handful of the ones shown here are orbiting with a very similar kind of trajectory. And what that implies is that they're actually gravitationally bound in a little group of their own. More exciting than that is not only that they're a group of their own, but that they are satellites of a satellite galaxy. So I showed you an image of the Large Magellanic Cloud earlier, and we believe that the Large Magellanic Cloud has a handful of its own satellite galaxies that were all doing their thing, orbiting around the LMC in the universe, and then that whole group of galaxies came into the vicinity of the Milky Way and became dominated by the Milky Way's gravitational attraction. So, satellites can have their own satellites. There's another piece of evidence of that in the Andromeda system as well. So it's a really exciting place to be. Now, up until now, I just have one more slide. Up until now, we've been talking about going backwards in time. With the kind of techniques I've talked about today, we can also go into the future. So many of you have probably heard of this splashy headline that's been around for a while now. But we believe that the Milky Way and our neighboring Andromeda galaxy will crash into each other in the future. Again, because we have an idea of the actual motion of the Andromeda galaxy. And so we can, in the same kind of way that we predict the past orbital trajectory, we can predict the future as well. So we think this will happen about 5 billion years from now. Not something we need to worry about. It's around the same time that our sun is going to explode and turn into a big ball of gas, or a bigger ball of gas than it already is. But this is the power of some of the techniques and the both combined observations and modeling and simulation techniques. This is the power of what we can do with them. So I will stop there and take your questions.